Hello and welcome to Mathematics with Simon. I'm Simon. Today we're going to look at a mathematics Olympiad question. We're going to look at the locus of this curve, x cubed plus y cubed plus 3xy equals 1. So we start with this observation that a cubed plus b cubed plus c cubed minus 3abc factorizes in the way that's shown on the right hand side. This is a really interesting result, and actually we covered it in a previous video. But it's a really interesting result, and one of the consequences of this is that if a plus b plus c is 0, then that means that a cubed plus b cubed plus c cubed minus 3abc is also 0, because the right hand side just goes to 0. So in this case, what we have is x cubed plus y cubed plus 3xy equals 1. So actually, if we choose a as x, b as y, and c as minus 1, then we can write this expression in the form above. We can write x cubed plus y cubed plus 3xy minus 1 as a cubed plus b cubed plus c cubed minus 3abc. What that then tells us is if x plus y minus 1 is 0, or x plus y equals 1, then a plus b plus c is 0, which lets us know that in that situation x cubed plus y cubed plus 3xy minus 1 is 0. So all the points for which x plus y equals 1 satisfy this equation. So they're all part of the locus. And we can just check this for some numbers. So xy is 0, 1. We get 0 cubed plus 1 cubed plus 3 times 0 times 1 is 1. For xy equals 1, 0, we get 1 cubed plus 0 cubed plus 3 times 1 times 0 is 1. And then for a half-half, x is a half, y is a half, we actually get a half cubed, and a half cubed is an eighth, and then an eighth, and then it's 3 times a half times 3 quarters, so it's a quarter plus 3 quarters. Sorry, 3 times a half equals 3 quarters. So we've got an eighth plus an eighth, which is a quarter, plus 3 quarters, which is 1. In fact, you can work it out generally for x comma y as z comma 1 minus z, and just crunch the algebra and show that that's always 1. Now, I'm not going to do that because in a sense I think perhaps that's replaying the algebraic proof I gave on the other side, but it's quite nice to see. So are there more solutions? Well, what we're going to do now is consider x plus y minus 1 as a function of x. So y minus 1 is a constant here. So this must be a factor of x cubed plus 3yx plus y cubed minus 1 when thought of as a function of x. And the reason we're putting yx in the middle there is because y is the constant and x is the variable. Normally we would write it as xy in alphabetical order. So by the factor theorem, this must be a factor. So we're just going to crunch the division now. So x into x cubed goes x squared times on top, and then you multiply x squared by x plus y minus 1, and we get x cubed plus y minus 1x squared. Subtract them, we get minus y minus 1x squared, and then we add 0x squared because the next term in x squared is 0. When we divide x into minus y minus 1x squared, and we get minus y minus 1x, we then multiply minus y minus 1x, this is like a tongue twister, by x plus y minus 1. We get the expression that we see below. Then when we subtract them, we get y minus 1 squared x, and then we bring down 3yx. We divide x into that, and we end up with y minus 1 squared, which is y squared minus 2y plus 1, and then we add 3y, so we get y squared plus y plus 1. And then we multiply that by x plus y minus 1, and we get the term at the bottom, which is y minus 1 squared plus 3yx, and then we get y plus 1, sorry, we get y squared plus y plus 1 times y minus 1, and that comes out as y cubed minus 1. Then we subtract and we get minus y cubed minus 1, and then we add on y cubed minus 1 and we get 0. So that shows that it's a factor. So now what we're left with this with the quotient, which is x squared, what was on the top of the division there, x squared minus y minus 1x plus y squared plus y plus 1. And that's a quadratic, and so we can use the quadratic formula to evaluate for x, but firstly we look under the square root sign, and we just simplify this algebraically. So we've got y minus 1 squared, which is going to be y squared minus 2y plus 1. Then we're going to take off 4y squared, 4y, and 4. And when we crunch all of that, what we get is minus 3y plus 1 squared. Which is very interesting because the only time that is non-zero is if y is minus 1. Otherwise, the only time it's non-negative is if y is minus 1. The only time it's 0 is if y is minus 1, but otherwise it's negative because y plus 1 squared is always positive unless it's 0. So we need y to be minus 1. And in the situation for which y is minus 1, we substitute this back in, so we get 0 under the square root. We just end up with minus 2 divided by 2, which is just minus 1. So y is minus 1, x is minus 1. Let's just substitute that in to check. So if we put x is minus 1 and y is minus 1, what we actually get is minus 1 plus 3, because it's 3 times minus 1, which is 3, minus 1, which is 0. So that point satisfies the equation. So these are all the solutions, which is really great. But going back to this factorization that we looked at earlier, there is another way which is very interesting, which is without doing the polynomial division. If we just use this substitution, a is x, b is y, c is minus 1, and we pop them in, what we end up with is x cubed plus y cubed minus 1 plus 3xy. So we're looking for this to be 0. So on the one hand, we've got this term x plus y minus 1, which we've already looked at, which is 0 when x plus y is 1. And then we've got this term on the multiplied by it. And this was a little trick. I don't know how I found this, but I enjoyed this. Is we take a half outside and then we double all of these terms inside. And then what we see is this is actually x minus y squared plus x plus 1 squared plus y plus 1 squared. And this is important because to make this 0, to make the left-hand side 0, you can either make x plus y minus 1 0, which we've looked at, or you can make this 0, x minus y squared plus x plus 1 squared plus y plus 1 squared. Well, that can only happen when all three of these are 0, because squares are always positive or 0. They're never negative unless it's the square of an imaginary, but these are real numbers. And or the square of an imaginary or a complex. But anyway, these are real numbers. Actually, this only works when all of these are... So you need y to be minus 1. You need x to be minus 1. So those two are 0. And then in that situation, x minus y is also 0. So it works only when x is minus 1 and y is minus 1, which is great. That's the solution we found earlier. I'm going to tidy up one thing I said earlier, actually, just to be super clear, which is if we want the square of a number to be negative, it has to be purely imaginary. If it's a complex number, it can't have a real part. Only purely imaginary numbers have real negative squares. So the positive reals have positive squares. The pure imaginaries have negative real squares. And then complex numbers, which are a mixture of real and imaginary, always have a square which is a mixture of real and imaginary. You can prove that as an exercise, but it's true. I hope you enjoyed that. I really enjoyed making it. Please subscribe and hit the notification bell if you want to see more. I'd love to hear your ideas, and most of all, I hope you enjoy your mathematics.